Okay folks, in this lesson we're going to take a look at the forces acting on a long straight wire in a magnetic field. We're going to discuss what magnetic flux is and what magnetic flux density is. Okay, so let's start with this situation. We have a wire that's coming out of the page, carrying current out of the page, stuck between a north and a south pole of, say, perhaps a horseshoe magnet. Now, before we get started, let's have a little bit of a diagram convention. This says I here for current, and there's a little dot. And that is because we're having to think in 3 dimensions here. If I wanted to draw you something going from left to right, I would simply draw an arrow going from left to right. Up and down is up, and down and right to left is like that. The problem is that I'm working now in 3 dimensions, and I have the third plane, I have the z-axis to concern. So I've got x and y sorted out with these arrows, but I need into and out of the page as to other axes. Okay, so the way I do that is I draw 2 little circles, right, and into those circles I will place 2 different symbols. If the object is coming out of the page, I will draw a dot in the center of that circle. It doesn't have to be red, but just for the sake of making it look like that. So this little dot coming out of the page is, if you imagine an arrow that's piercing through the paper, the first thing you would see would be the tip of the arrow. Okay, so this is the tip of the arrow coming through the page. And for an object going into the page, we put a little X. If I can draw an X properly, in fact, I'll draw it as an X here. So I place an X into my circle. And the reason for that is, imagine an old style arrow with its fletchings in the back. Okay, the little feathers on the back of it. If you were to fire an arrow into the page, the last thing you would see going through the page would be the rear of the arrow, which would look like that. So this is out of page, and this is into page. Okay, so what we want to do is we want to quantify how large a force a particular wire stuck between a north and a south pole with current flowing through it would experience. Okay, we should already know that that a wire carrying current is generating its own magnetic field, and that we're using the right-hand grip rule to work that out. Okay, if not, take a wee check at your notes previously and have a look at that. So this wire is itself forming a magnetic field. That magnetic field is coming through this one, and because we're going to have 2 magnetic fields interact with each other, there's going to be a force. So let's draw in our lines of fields we've got going on here. We've got the north-south field here, which is traveling from north to south between the poles of these 2 magnets. Okay. We also have a circular magnetic field that's coming along with this wire. Okay, and that magnetic field is circular around that wire and is rotating in this direction. Now, we're not going to draw that in for the sake of this because we're going to make our diagram a little bit too complicated. Now, what we want to do is we want to figure out which direction this wire is going to be forced in. What is the direction of the force acting? Because there's definitely going to be a force. So which direction does it go? And to do that, we're going to use Fleming's left-hand rule. Okay, so what you need to do is you need to get your left hand and you need to hold your fingers like this. So that is, your thumb is vertically up in the air, your index finger is extended completely straight, and your middle finger is at right angles to both of them. So it's kind of looking horizontally. If you're pointing your thumb up, your index finger, say, to the right, then your middle finger should be pointing towards you. Okay, so that's how this works. Okay, and it's just a little aide-memoir because the basic idea is that the force is perpendicular to both the current and the magnetic field that it's entering into. Okay, so how we use this then is we use the FBI principle, which is F here, B here, and I there, because you're forming a little gun, and it's the FBI coming to get you. Where F stands for force, so it's the direction of the resultant force that's going to happen to you. B is the magnetic field direction. And I hear you wondering why we're using B. Well, B is a symbol for magnetic field strength, and we're going to get really familiar with that in the coming lessons. So it might be a little bit odd now, but give it a week and it'll be completely second nature to you to refer to B as magnetic field strength, and I is current. Okay, so FBI. Now what you have to do is you have to line your hand up in the direction of all of these things. Okay, without moving your fingers. You're allowed to rotate your elbow, your wrist, whatever, but you cannot move your fingers from that orientation. So what we need to do is we need to align our index finger in the direction of the magnetic field, north to south. We need to align our middle finger in the direction of the current, which will be coming out of the page, so it should be pointing towards us. And then our thumb should automatically line up in the direction of the force. So let's try that. Let's take our little hand here, and we'll do our magnetic field first. So we'll rotate our hand around like this, and we have our magnetic field pointing downwards. Let's increase the transparency of this image so we can see both at the same time. Okay, so I'm pointing downwards with the magnetic field. My current is coming out of the page, so my finger should be pointing towards me, and it is in this diagram, so that leaves me with my thumb automatically this way. Okay, so the result here is then that the wire is going to be forced this way, and we can say that this is the direction of the resultant force F. Okay, and in any situation, that's how you find the direction of the force acting on a charge or a current that's traveling through it. Now, it's really important that you understand that when we're talking about current, we're talking about conventional current, so that is the direction of flow of positive charges. Some very nasty examiners might send something like an electron flying through here, in which case you have to realize that the movement of an electron is in the opposite direction to that of conventional current. Okay, we might take a look at an example of that later. Alright, that's lovely. We've got the direction of the force, but we've no idea of the size of the force. We're going to need a little bit more information in terms of this, because it turns out that the size of our force depends on a few things. Okay, the size of our force actually depends on three things. It depends on, number one, it depends on the strength of the magnet, which doesn't seem particularly weird or odd. You put a current through a strong magnet, you would expect there to be a larger force exerted on that current than if you put it through a weak magnet. That seems straightforward. It depends on the amount of charge flowing. Again, that doesn't seem particularly weird, that if I've got a huge amount of charges flowing through, each of those are going to interact with that magnetic field. Each of them are going to experience a force. The overall force should be larger, simply adding them up. And thirdly, it depends on the speed of the charge. Where if an object is coming screaming in and suddenly gets knocked to the side, it's going to be knocked a lot more than if something's just gently drifting through. Okay, it depends on the speed of the charge. If you've got lots and lots and lots of charges, it depends on their average speed. Because if you've got something like a wire here and you've got current coming towards you, then it's true that most of the charges are coming towards you, but some are traveling the other way, and there's an average speed coming along here. And this is sometimes called the drift velocity of the charges. Okay, so in this example we have a magnet of strength 20 millitesla, has a wire of length 2.2 meters traveling through it, and it is carrying a current of 2.5 amps. So what is the force exerted on the wire is what we're interested in finding out. So F equals BIL is our equation. So it's a straightforward pop the numbers in. We've got 20 times 10 to the negative 3 for our force. We're going to multiply that, put that in brackets, multiply that by our current, which is 2.5 amps, multiply that by our length, which is 2.2 meters, and we just fire all of that into a calculator. So calculator's on standby. We do 20 times 10 to the negative 3 multiplied by 2.5 multiplied by 2.2, giving us an answer of 0.11 newtons. Okay. And we'd need a diagram, or we'd need something else to be able to work out the direction of that force. And the direction of that force would be calculated using Fleming's left-hand rule. Okay. Now let's take a look at that in a slightly different scenario. Let's have a look at something like this. In this situation, what I've got is I've got a north pole and a south pole facing opposite each other, and in between it I have a loop of wire where I have a positive terminal here and a negative terminal here, and the current is going to travel around this loop like this. Now, here's the fun bit. Can you work out using Fleming's left-hand rule what's happening on this side of the wire? Okay, so on this side of the wire we have our current traveling up the page, so we take our hand and we arrange it in such a way that our index finger should be pointing, or our middle finger, sorry, should be pointing directly upwards towards the ceiling if you're looking at the screen here. Your pointy finger should be pointing from north to south. That is, your index finger should be pointing from left to right. And as a result, you should find that your thumb is automatically pointing into the screen. So the direction of the force is into the screen here. So we know that the force is traveling in this direction. We have no idea about the strength because I haven't given you any numbers to deal with that yet. On this side, however, the current is traveling down the screen. So again, we take our left hand, our middle finger should be pointing vertically downwards. Our index finger should still be pointing from left to right because it's still north to south here, which means that my thumb is now suddenly pointing towards me, which should give me a force traveling out of the page. Now, the super inquisitive amongst you should be like, well, what's happening here? I've certainly got current traveling across this top bit, but if I try to arrange my left hand in such a way that my current is, my middle finger is traveling left to right and my index finger is also traveling left to right, I can't do that by moving just my wrist. I have to bend my fingers, and that is because you only get a force for the components that are perpendicular to each other. And since this current is now along the direction of the magnetic field, there is in fact no force applied. Okay, so there's no force along this bit. But we do have a force into the page on this side and a force out of the page on this side. And that's going to cause a rotation. Now what we're going to get is we're going to get a curve where this side is going to travel upwards out of the page and this side is going to travel downwards into the page. And the result is that this whole thing is going to spin. This is the basis of a DC motor. Direct current motor because the plus and minus is traveling around here. Now, the problem with that is that when this rotates over, then this side comes over to here, this side goes over to there, and it starts to oscillate and jumps back and forward. So what we need for this side to always be connected to the positive and this side to always be connected to the negative. Because as soon as this side travels downwards and over here, then this side's going to become positive, this side's going to become negative, and the whole thing's going to come back. So what we need is a system where one side stays positive and the other side stays negative. And we do it like this. We have a battery, positive side, negative side, connected to two little brushes. Okay? And these things just touch these wires here. They aren't actually connected, they just touch them. So that when this starts to turn, all these black bits lose contact and flip over. So a little time later, the whole thing is actually vertically upright, so it looks just like this. Okay, not connecting anything. But then it falls back over again and ends up in this situation again. This is called a commutator setup, and these little bits here, are contact brushes. These are called brushes. And they allow you to maintain this side is always positive, because this side doesn't move now. And this side doesn't move, just the wire flips over. So it gets a kick when it touches here, flips itself over, and then gets a kick again and again and again and again and again. So its own momentum carries it round in through each bit, but it's only receiving a force when it's in this horizontal kind of setup. Alright, so that is the basis of a DC motor. Onwards we go then to the idea of flux and flux density. Okay, so let's get ourselves a couple of magnets. Okay, so let's get a magnetic north pole here. I'll fill that in red. And let's get ourselves another one over here for fun, for comparison purposes. And let's get a couple of south poles as well. So we'll copy those down and we'll change their color. Alright, so we've got these. Let's draw in their magnetic fields. So we've got field flows from north to south. So there's a field going on, relatively uniform. Now, let's play spot the difference in these diagrams. Okay. Well, the simple difference is that this one has a few arrows and this one has lots of arrows. And as with all field diagrams, the arrows and the density of their packing represents the strength of the field. Okay, so field strength is proportional to arrow density. And that's fine, provided I'm working in the same book and I can compare these two things. right? That as you've got these two things side by side, you can go, right, well, okay, he clearly means that this magnet is less strong than this magnet. Okay, that's obvious. We'll just probably lined in the middle so that we understand they're not interacting with each other. But what if this diagram was in a different textbook to this diagram? Well, it might be that the two authors just have different ideas as to what magnetic strength is, because this could be a particularly strong magnet in reality, but it might be that in the context of the book, it's a weak magnet compared to the other magnets that this author might be discussing. So say this author here is maybe discussing, industrial magnets. And you, okay, brilliant. Brilliant title, excellent book, I recommend it to everyone. Whereas this one is discussing super small magnets and me. Okay, so this person has suddenly got, well, imagine a really strong super small magnet. Well, a really strong super small magnet is still going to be crap by comparison to a weak industrial magnet. But because these two people are writing different textbooks, these diagrams make sense in their own context, but when they bring them together, they don't make sense at all. So we have to do something about that. We're definitely going to have some form of convention for how this operates. And how we do that is we define something called magnetic flux. And magnetic flux, let's just write that down as a new keyword. Magnetic flux is simply a measurement of the number of field lines that would be made on a standardized diagram. Okay, so it's absolutely fine for these authors to draw these diagrams. Okay, but this person's going to have to tell me that the magnetic flux here is, say, 25 on this side, and this person will tell me that the magnetic flux is actually like 2. Their diagrams are okay for comparison purposes, but now I can compare across that. So magnetic flux gets given the symbol phi, okay, and it is measured in units called Webers, WB, Webers. Right, and all it is it's a measurement of the number of field lines. So if I say 20 Webers, it doesn't actually mean anything. What it means is, though, that if you were to draw a diagram of magnetic flux, the 20 Webers diagram should have 20 times the number of field lines that a 1 Weber diagram would have. Okay, so that's all it is. It just tells you about the number of field lines, and in itself is not a particularly useful unit. However, it does become extremely useful a little bit later. That if I were to go and say, right, how many field lines are there in this area here? All right, so let's fill that in there. How many field lines are actually traveling through that area there? And then I would get number of field lines over a given area. And that would give me a measurement of the density of the field lines. And as with all field diagrams, the density of field lines at a given time is a measurement of the strength of the field. Okay, so the strength is equal to the density of field lines in an area. And because we now have a standardized unit for how many field lines there should be, and area is already a standardized concept in terms of meters squared, we can say that the strength of a magnetic field is equal to the number of field lines, phi, divided by the area A. All right. This leads us to a much more useful concept of magnetic field strength, and that is the magnetic field strength B is equal to phi over A. Okay, or written nicely, it looks like this. B equals phi over A. So this is our magnetic field strength equation. B equals phi over A. Okay, so let's define some of these terms. This is magnetic field strength, B. And it is measured in Tesla. Okay. This is the number of field lines that we get. Okay, now we can't just call it number of field lines, we give this a special name. So we call this magnetic flux. So magnetic flux is the number of field lines you get standardized in terms of Webers. And it's measured in Webers. And this is the area over which your magnetic flux is flowing through. Okay, so what's the area that your lines are traveling through? And that's measured in, as usual, meters squared. Now, since this is then magnetic flux per unit area, magnetic field strength is also sometimes known as magnetic flux density. Okay, and this is really important because it's super confusing. Okay, it's still in Tesla, but it has the word flux in it, and people get confused an awful lot. Magnetic flux is measured in Webers. It is the number of field lines passing through a particular area that you choose to do it. And all it is it's a standardized measurement. Okay, it's if you were drawing the same diagram as everybody else, how many field lines would you need? Magnetic flux in Weber. Okay, once you divide that by the area that it's traveling through, though, you get a different number. You get Webers per meter squared, which is the magnetic flux density, and that is measured in Tesla. Okay, I hope that makes sense to you. So let's try a little example question here. So let's try example. And it is generally just a question of popping some numbers into a formula. So let's try a flux of 30 Webers is traveling through an area of 150 meters squared. That's 30 Webers, quite a lot of flux. What is the magnetic field strength? Okay, and the answer here then is that we use that B equals phi over A, so B equals, change to phi divided by A. We'll pop our numbers in, so B equals 30 divided by 150. So B equals 0.2 Tesla. Job's a good one. So the magnetic field strength, or the magnetic flux density, is 0.2 Tesla in this one. And I think that's quite enough concepts for today, so we'll wrap it up on this one. There's some little questions in the description below. Have a crack at those. I'll see you in the next one. And oh, just before you forget, physics rocks. It's true.